All right, so like I said, chapter one, functions from a calculus perspective. We're going to be looking at functions. This is going to be a lot more algebraic, but it's kind of a more in-depth view of functions and stuff that's going to get you guys ready for higher level math or calculus or whatever classes you guys are taking. Section one, what we're doing today is just on functions. And we're not really going to get all the way into all the function stuff today. A lot of what we're going to go over today is going to be notation. We're going to talk about sets of numbers because there's going to be different sets of numbers that we talk about, like natural numbers, whole numbers, integers, rational numbers, real numbers. And so you guys may be vaguely familiar with some of that. We're going to go over that a lot more in depth. And then set builder notation is a notation that we're going to use a lot throughout math analysis. So we're going to cover that, and then also interval notation today. Okay, so the first thing that we're going to talk about, I'm going to go through the list of kind of all of our number types. So the first one is real numbers. So real numbers, and most of our classes of numbers have a symbol. So for real numbers, it's kind of a boldface R like that, just kind of has the double line up and down. And then I'm going to list some examples out here next to each set. Real numbers basically include everything except imaginary numbers, and that's what you normally think of when you see a number line with like a solid interval. Okay, if it's like everything between 0 and 1 would include all real numbers, kind of like that solid like shaded area. So this would include things like positive and negative whole numbers, fractions, decimals, but also irrational numbers like square root of 7, pi, basically every type of number that you can think of except for imaginary. And then the next set that we're going to talk about is integers. And for integers, we use a capital Z, because an I actually is for imaginary numbers. So integers, we use a Z. And integers are basically positive sorry, I skipped one. Integers are positive or negative whole numbers. So I should have done this before integers. The next one is rational numbers. And the symbol for rational numbers is Q, again, because R is already being used. And I'm just going to put an arrow over here because it doesn't matter too much, but technically rational numbers is like more broad of a category than integers. In rational numbers, how I remember those, I look at the prefix or the root word there, ratio. Rational numbers are anything that can be expressed as a ratio of two numbers, A over B. Okay, so that's like all of your fractions. Now, rational numbers don't have to be just fractions. So I can have positive or negative fractions, but it's also anything that can be written as a fraction. So any of your decimals that are terminating or repeating. So for example, 0.25, any decimal that terminates can be written as a fraction. So even if it has like 5 decimal places, if it was like 0.12345, you can turn that into a fraction. Okay. Also, if it's a repeating decimal, like 0.3 repeating, yep, is a third. Any repeating decimal can be written as a fraction. Also, all of your whole numbers could be written as a fraction or as a ratio. You can put that as -5/1, right? So all of these are rational numbers. I generally think of it as fractions, but it's anything that can be written as a fraction. Okay? Oh, and just one thing I'll point out, that's why this should have come before, because your real numbers are like the broadest, so this has all your rational numbers and irrational. Then it would be rational numbers, and then it would be our integers, positive and negative. And then the next one would be whole numbers. Which we use a W for that. And whole numbers are the same as integers, but only 0 and positive.
Wait, why would negatives not be considered whole? I never understood that.
I'll discuss that in just a second, but. And then lastly, here we have natural numbers. Which is the same as whole numbers, but only starting at 1. Okay, so to answer your question, Brody, the reason why whole numbers don't include negative numbers is it's really just different classifications of numbers that came about at really different periods of time. So for example, natural numbers here would be essentially like the most primitive number classification. These are sometimes referred to as counting numbers because if you're just counting physical things, you don't even need 0, right? You're just going to have 1, 2, or 3.
Isn't it also called like ordinal or something, or is that something else?
I don't know about that. I've heard them referred to as counting numbers. But natural numbers, think about you're just counting physical objects. You don't even need a 0. Okay. So this was essentially probably the first number system. Might have been, had different notations for even the numbers, but just some type of counting system. Later, for whatever necessity, different groups of people decided that, hey, it's worthwhile having a systematic notation for 0. Because until, before then, if you're just counting objects, you don't need a 0, right? A 0 is just nothing. You don't need a number for that. Well, as need arises, people have devised different number systems, so then we added a 0.
Yeah, I think
and that's your
in India that they used that first.
Yeah, there's actually a lot of stuff that was kind of developed parallel at different times in different places. But anyway, your whole numbers include 0. That would be kind of the next evolution of the number system. Integers came about once we needed negative numbers. So it's not necessarily that these numbers are whole as like a whole number with no fractions, and these are not. It's just a different classification that came about at a different time. Okay? So yeah, we would go natural numbers, then whole numbers where we added a 0, then we added all the negative numbers, and then your rational numbers involves all of your ratios. So once you start dealing with any type of measurements, so that would be when you started more agriculture and needing area, perimeter, dimensions for building things. Anytime you have a measurement, as soon as you define any sort of metric as, this is 1 yard or 1 meter or 1 foot or 1 anything, well, then you have to have fractions of that. And then you need that all comes from ratios. 1/2 is the same as 1 divided by 2, or the ratio of 1 to 2. So that's why they're called rational numbers with that root word ratio. Okay. So as need arose, we developed new number systems. And then sometime later, irrational numbers were discovered. This actually came about from triangles when they looked at Pythagorean theorem, when they figured out how to calculate right triangles. They basically said, hey, if we have a triangle with sides of 1 or legs that are 1 unit each, and they tried to figure out the hypotenuse, and they couldn't make it an even ratio of any unit. And so then they discovered, hey, the square root of 2 must be irrational. And so then the real numbers evolved to include all of those. Okay, so now what we're going to do to kind of organize and help us understand all that, I'm going to make a chart because we were going to be talking about sets in this class a lot. And so sets, a lot of times we organize visually with charts and graphs and stuff. So what I'm going to have you guys do is, if you've got room out to the side of that list or wherever, we're going to make a table that's going to have 2 columns like so. Actually, but up at the top, this is going to be 1 thing. Because across here, we're going to have complex numbers. Okay, and complex numbers include everything. There is no number that is not a complex number, at least as of yet, until some new number system gets created. But complex numbers include everything that is just a real number, an imaginary number, or the complex numbers that could be just like a combination, like 2 plus 3i. Those are all complex. But complex numbers include real numbers, which I'm going to put over here, and imaginary numbers over here. Okay? And those two things are separate, so there's no overlap between real and imaginary numbers. But then this is kind of going to be a concept that we talk a lot with sets, okay? Imagine this rectangle is the entire set of real numbers, okay? Within that, you have what we call a subset, okay? And that subset is going to be rational numbers, which is Q. Okay, every rational number is also a real number, right? Our rational numbers were all those fractions and decimals, right? Every rational number is also a real number. But not necessarily is every real number rational.
Yeah.
Is everybody good with that? Yeah, everything out here would be irrational, like your square root of 2, square root of 7, pi, stuff like that. Okay. But then we have a subset of rational numbers, and that is integers. Okay. So out here we have all of your fractions and decimals. This includes your integers, and then here we just have our positive or negative whole numbers, which is our integers. And then inside of that, we have whole numbers. And then the very, very smallest group is natural numbers. Sure that we understand this correctly. Every natural number, so everything in this set of natural numbers is also a whole number, is also a integer, is also a rational number, and so on. So if it belongs to a smaller subset, it's also part of every bigger set that belongs to. Okay? Not everything out here, though, is automatically part of these smaller subsets. Okay? So, for example, Q is what? Rational numbers. Okay? So, give me an example of a rational number that is not a integer.
Half.
Okay? 1/2, right? That'd be a rational number, but not this. Give me an example of a real number that is not a rational number.
The square root of 3.
Square root of 3. Square root of any number that's not a perfect square, so like square root of 2, square root of 5, square root of 7, are all irrational numbers. Okay, so that's it for the table. All right, so the next thing we're going to talk about, we've got two types of notation to go over. First is going to be set builder notation. Okay. And set builder notation is really used to define the characteristics of a set. So our sets always use brackets. So I'm going to give you a set here. Okay. Now, set builder notation and the other notation that we're going to talk about here in a second, both kind of have their pros and cons. Normally, I probably wouldn't use set builder notation for this, but we're going to start simple. A lot of times set builder notation is necessary for when we have infinite sets to be able to describe it without having to list everything out, okay? And then it will be able to describe it in a kind of brief, concise way without words, just using notation. Well, let's go ahead and do it on this one. So I'm going to label some of the stuff after I write it. But set builder notation is always going to use brackets. And then we're always going to use a variable, generally x, followed by a vertical line like that. Okay? And basically, this means the set of all elements x such that and then that vertical line kind of separates it, and then over here we're going to list out the properties of all of those elements of x. Okay, so the first thing we're going to do here is this set is kind of restricted to numbers between 2 and 7. Okay, so we're going to write an inequality to restrict that. So x has to be between 2 and 7. So I'm just going to use a compound inequality. So x is greater than or equal to 2, less than or equal to 7. And then we can put a comma, and then we can have more properties after that. Okay. So the next thing that I'm going to do, usually an inequality indicates real numbers or like a continuous interval, right? This is everything between 2 and 7, okay? I don't want everything between 2 and 7. I want to restrict it to those whole numbers, or actually in this case, they're all natural numbers. So the second kind of criteria that I'm going to put is that x is an element of the set of natural numbers. Okay, and we'll talk about this. So here, this symbol is the Greek letter epsilon. We're going to use that a lot. It's like an E, but it's more curved. It's more like drawing a C with a line in it. So that symbol epsilon means is an element of, or kind of a little bit shorthand for that is belongs to. So real quick, I'll just go through this and kind of read, because I read this almost like a sentence. So how I would read this, it'll always start out with this. So this is the set of all x such that x has these properties. So then you list out the properties over here. X is between 2 and 7, so that's what restricts kind of the interval. And then x is an element of the set of natural numbers, or what I generally say is x belongs to the set of natural numbers. Okay, so I usually kind of go with this one. It's just shorter and easier to say, and is sufficient. Okay. Okay, so let's go through this. Again, I would probably not generally use set builder notation for this problem. I would probably use our other notation, but we're going to do it anyway. So for set builder notation, start with your brackets. So we've got the set of all x such that, I'm just going to start out with x is greater than negative 17. Hey, that's the interval that we're on. And then also that x belongs to the set of
Real?
Yeah, so if it does not specify, inequalities generally indicate all real numbers, because it's just, if you think about shading on the number line, it's just everything on that number line, right? Which includes all your rational numbers and irrational numbers. And then we close it with our brackets. This next one, I think, is where set builder notation is a lot more practical. Most of the time, if you just have a solid range of real numbers, the next thing we're going to do is a little bit more practical. But if you have something that's not a solid range, okay, if there's like skips in it or there's some type of pattern, set builder notation is a lot more practical. So this next one, we're going to do all multiples of 7. Okay. So this is actually something that we do a lot in math with set builder notation. So it is the set of all x such that, and then we need to write something that's going to define this as being a multiple of 7. And how we generally do that is if x, so all of our elements x here, if they're all multiples of 7, that means they have to be 7 times something.
So it'd just be 7x.
So not 7x, what we're going to do is x is equal to 7 times a number n, and then we're going to specify that n belongs to the set of integers.
Integers, really?
Mm-hmm.
What multiplying, like,
So what we're going to look at here, if I just look at this part, if n is an integer, which is what we specified, then 7 times any integer is going to give you a multiple of 7, right? If I put 1 in for n, I would get 7. If I put 2 in for n, I would get 14. If I put 3, I would get 21. I can go in the negative direction, but that's going to give me all multiples of 7. There's no way I could ever list all those out, right? Because it's going to be infinite, but I can describe it using properties here.
I think it might remember what this one is.
So interval notation. Interval notation is much, much more useful for describing that range of like numbers on a number line, real numbers, kind of like what I was saying that set builder notation wasn't that great for. So if I've got like everything on a certain range, interval notation is much more beneficial for that. So let's start with something like that, where I've just got an inequality.
This was,
Okay, so one thing I want to talk about here, this compound inequality, hopefully we remember a little bit from Algebra 1. Kind of a very simplistic way to think about it is that x is everything in between -2 and 4, and then you just have to pay attention to the signs. It's actually a compound inequality. It means x is greater than -2 and x is less than or equal to 4. You can kind of split it apart like that. I'm going to show it to you graphing. You don't actually have to graph at all on these, but just visually, I think for the first time, it's helpful to see. This would be all numbers on a number line from -2 to 4. And if it's not equal to, that would be an open dot, right? It cannot be equal to -2. But it can be equal to 4, and it would be all real numbers in between. Okay? So interval notation basically describes this interval of numbers. It has to be a continuous interval like that, solid, all real numbers, but you just put the smallest number in the interval and the biggest number in the interval, and then you use parentheses or brackets. So if it is equal to, you use a bracket, and if it is not equal to, you use a parenthesis.
yeah, I remember having to do that.
Okay. So that just, if I look at this, this means the interval from -2 to 4, equal to 4, not equal to -2. Okay. All right, so next, you have x is greater than -5. And so if you think about that interval, it's kind of an open interval. It keeps going, right? Okay, so the smallest number in that interval, so I always think about it, even if I don't graph it, I just think about it on a number line. I've got -5 and up, right? So the smallest number in that interval is -5, parenthesis or bracket here.
Parenthesis.
Okay, and it's going to keep going to infinity. And a number can never actually be equal to infinity. It's more of an idea. It's just going to keep going and keep going, but there's always going to be another number. Think about it. If you keep adding and adding and adding, you're just going to get bigger numbers. You're never actually going to get to infinity. So anytime you have infinity, it's always going to be a parenthesis. Okay.
It works both ways.
Okay. So if we have x is less than 3 or x is greater than or equal to 12, The solution is actually the solution set of both of those put together, right? Think about -4 or 0 would be a solution, and also like 15 would be a solution as well, right?
But not positive 4.
Correct. So what we're going to do here, you're going to write interval notation for this interval. So think this is going to be everything from -infinity up to 3. So -infinity to 3 parenthesis. And then we use a union symbol, which is like a U without the tail. And it's union, which means to like put together with the interval here, which is going to be 12 to infinity. Of course, parenthesis on the infinity, and then we have a bracket on the 12.
That's what took me forever to get when I was taking my college algebra.
Okay. Real quick, union means to put together. So if I have like a set A and a set B, the union of the two sets just puts them together, and it's the entire thing. Okay. So here I have this set and this set, and if the solution is both of them put together, so I use a union. Okay, that is it for notes today. So we've got set builder notation and interval notation. Your guys' assignment is on page 9, I believe. Yep, page 9, 2 through 14.
Can you go over another